Hey everyone, and welcome to today's Explainer. I am honestly so pumped for this one. We are diving deep into a comprehensive visual review of a stunning digital asset, basically a complete Obzor 3D model. We're going to strip away the magic and look at the intense technical groundwork, plus the incredible artistry that goes into making something like this. If you've ever looked at modern movies or games and thought, wow, how does that look so incredibly real? Well, you are definitely in the right place. Let's just jump right in.
Just take a second to look at this. Look at the beautifully worn leather wrapped tight around that grip. Notice the subtle little gleam, the tiny imperfections on the gold crossguard, and that cold, scratched steel resting on the rich wooden desk. It looks heavy, right? Like some ancient relic you could literally just reach out and grab. But here's the crazy part, the mind-bending secret. Absolutely none of this physically exists. No leather, no gold, no steel, no wood. It is entirely a masterpiece of pixels, just a brilliant illusion of reality calculated by a machine. Pretty wild, right?
All right, Section 1, Introduction to the Digital Blade. Let's take a look at the pipeline journey.
So to really appreciate the final product, we have to pull back the curtain a bit. Look at the direct contrast here. On the left, you've got this solid, flat, gray viewport mesh. It kind of looks like digital clay, right? Completely devoid of life. But then on the right, you have the highly polished, fully textured final render. Every single gorgeous detail on the right side was painstakingly painted and programmed onto that blank canvas on the left. It's an absolutely spectacular transformation. And honestly, understanding exactly how we get from that raw, blocky geometry to the polished masterpiece is what makes 3D modeling so incredibly fascinating.
Moving on to Section 2, let's do a quick analysis of the geometry and wireframe. It's time to look under the hood. Okay, so this right here is the polygon skeleton. It's the full wireframe view of our model. Look at that insanely complex network of intersecting lines and vertices making up the 3D asset. You see, before a computer has any clue what leather or metal is, it only understands math. This wireframe, it's the absolute mathematical base of our sword. Every single little line, what we call an edge, connects 2 points in digital 3D space. And when you connect 3 or more of these edges, boom, you get a face or a polygon. There are literally millions of calculations happening right in front of you just to define the basic silhouette of the weapon.
Let's zoom in a bit and focus right on the hilt. Do you notice how the density of those black lines, the mesh, just dramatically shoots up around the curved pommel at the bottom and along those swooping, elegant curves of the crossguard? You might be wondering, why do that? Well, in the 3D modeling world, straight lines are super cheap and easy for a computer to draw. But curves? Man, smooth, realistic curves require massive amount of geometric data so they don't look all jagged and blocky. The artist actually concentrated the geometry right here, purposefully, to keep those perfect smooth shapes without overloading the simpler, straighter parts of the blade.
And really, this perfectly illustrates why clean edge flow and proper polygon density are absolutely critical. It's a make-or-break kind of thing. Because if this underlying skeleton is messy, like if the lines don't logically flow along the shape of the object, the final model is going to fail, period. The computer uses these lines to figure out how virtual light should bounce off the surface. So a bad wireframe means the light catches on these invisible bumps, and you get these weird, strange shadows and visual artifacts. It instantly shatters that illusion of reality we're going for. Honestly, good topology is the unsung hero of 3D art.
Which brings us to Section 3, detailing the grip and guard. Let's talk about surface beauty.
Check out this incredible close-up of the diamond patterned grip and that golden crossguard. Notice the wear and tear on the metal? It is not perfectly shiny. There are microscopic scratches, little smudges, even areas where the polish looks like it's worn away from a human hand rubbing against it over years of use. Same thing for the leather. It's got this bumpiness, a porous texture that catches the light totally differently than the metal does. In the 3D world, we achieve this through something called texture mapping. Essentially, artists wrap these highly detailed digital images around our wireframe skeleton, and that tells the computer exactly how rough, metallic, or colorful every single pixel is supposed to be.
Now, as we pan up the weapon, look at how this detail continues to build along the blade itself. I really want to focus on the metallic reflections inside that central groove. Historically, that's called the fuller. Pay attention to the microsurface detail there. The steel isn't just a flat mirror. It actually looks forged. It has this super subtle, uneven grain to it, perfectly mimicking the hammer strikes and the grinding wheel of a blacksmith. And the way the light streaks right along the edge of that groove, it just gives the blade this feeling of supreme sharpness and lethal intent. It is masterfully done.
So the really crucial takeaway here is comparing that structural wireframe directly to the fully textured model. That mathematical skeleton on the left is precisely dictating exactly where the leather, the gold, and the steel materials wrap on the right.
Notice how the horizontal loops of geometry on the grip line up perfectly, and I mean perfectly, with the metal rings separating the leather. It's like a giant digital puzzle where the math and the art are just working together in complete seamless harmony.
All right, Section 4, Textures, Materials, and Lighting. This is where we breathe actual life into the 3D model. Now take a look at this comparison. We've got the exact same sword model here, using the exact same textures, but it behaves completely differently depending on the lighting setup. On the left, the sword is resting on a dark wooden desk. You can see the metal actually reflects those warm, rich browns of the wood, which makes the steel feel a bit warmer and deeper. But then, look on the right. The sword is sitting in a harsh, bright gravel environment. Suddenly, the steel is reflecting the bright sky and those gray stones, giving it these really cold, sharp, high-contrast highlights. This technique is called HDRI lighting, where an entire 360-degree image lights the scene. It really proves that a digital object is only ever as realistic as the virtual environment it lives in. But lighting isn't just about the reflections, it is heavily about shadows. Notice the soft, incredibly realistic shadows casting directly onto that wooden desk? Look right underneath the crossguard in the grip. That shadow is the exact thing that anchors our 3D model into the scene. If that shadow wasn't there, the sword would just look like it's awkwardly floating in empty space. By calculating exactly how the light gets blocked by the geometry we were looking at earlier, the computer generates the shadow, and that completes the ultimate illusion of physical weight and gravity. It totally grounds the asset in reality. Which actually brings us to a final question for you to ponder today. We've looked at the raw gray mesh, we've explored the intense mathematical wireframe, we've admired the hand-painted textures, and we've analyzed the simulated light and shadow. Knowing all the math, all the art, and all the clever trickery that goes into reviewing a 3D model like this, can you still tell what's real? As digital craftsmanship just keeps blurring the line between pixels and reality, how easily are we going to be able to distinguish the physical world from the digital one in the media we consume every single day? It's definitely a fascinating thought to leave you with. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you in the next one.